Ah, we'll be fine. Not today. All right, here we go. So we are starting a new unit in static electricity. This is a um, very different than what we've studied so far. This chapter, next chapter on circuits and magnets, next chapter after that, um, have common threads between them. So by the time in this lesson, you'll be able to describe what happens at the atomic level to conductors and insulators, next to charged objects, and describe different ways will be charged. We'll do that part 2 tomorrow. So quick chemistry review. What are found in the nucleus of an atom? Protons and neutrons. Electrons are charged what?
Sorry to interrupt. I was just going to ask if you have any more seniors teacher papers.
There you go.
Thank you.
You're welcome. And what are the charged particles responsible for bonding? Electrons. Good with that? Yeah, you do. Lewis dot structures. Make sure you have your 8. Make sure you turn off your phones. Almost done. Positively charged is if you have more what than what? More protons than electrons. Negatively charged have more electrons than protons. If you're neutrally charged, you are equal number of protons and electrons. Okay? In this class, we do not care about neutrons. They just add mass to stuff. Don't care. If two objects are brought near that have the same charge, what happens to them? They repel. If they're oppositely charged, they attract. Okay. Conservation of charge simply states in interactions, charges are not created or destroyed. They're just there. Like they're just rearranged. So you did that when you were doing chemical reactions and balancing equations. You took into account all the charges that were there. They weren't created or destroyed. Good with that? So, chemistry review. Okay. So, the thing that you need to watch for, like remember, electrons are where it's at. Electrons are the thing that moved or transferred. That's what happens. Okay? Electrons. Electrons are the moving thing, and they are the thing that will do stuff. So, an electric conductor, give me some examples. Electric conductors. Copper. Well, yeah, metals. Okay, we're good with that. Okay, what do conductors do? Allow electrons to transfer easily. Allows electrons to transfer easily. Microscopically, anybody have okay. Microscopically, here's what goes on. Your periodic table has the 2 twin towers. In the valley in the middle is the transition metals. Okay. This metallic bonding has a phrase in chemistry called sea of electrons. Okay, when they bond, it's kind of like a commune or a hippie community where everybody shares the electrons. It's like, hey man, my electron's your electron, dude. Yeah, man. Hey, could I have a couple electrons? Sure, dude. Like, hey, do you want any more of it? Yeah, I'll take. Sure, man. Like, can I come up? Yeah. Like, a big happy community. As long as they're all there, everybody's good. Okay. Insulators. Give me some examples of electric insulators. Rubber. Air is. Ish. Okay, so rubber. Fiber. Yeah. How about plastics? Yeah, it's okay. It yes. Yes. It's not I wouldn't qualify it as an insulator, just not a
Are you saying that because it's not a solid?
no. You can dissociate just like
Dissociated by name.
it can like just like air, you can like rip electrons off.
But like, are liquids and gases not as good at electric? Like, do they not use them as electric insulators ever? Like, do they ever use?
Yeah, no, I know, I follow what you're saying.
Do they ever use them as
Rare.
electric insulators?
No, because the solids are more readily available and they're better.
But there's aerogel. What about like aerogel? Oh, dude, I love that stuff.
Oh, let me put aerogel around my flag well.
Well, yeah. I mean, it works.
I don't want my hands to be sticky for it.
It's not. It's just. You can make it into
Okay.
a solid or not.
I'm not totally sure if there's exceptions of those. Okay. Insulators. They do not allow electrons to transfer readily or easily. We'll do it easily. Okay. So, the reason why microscopically is because they are possessive of their electrons. This is where you get your happy 8. Okay, you fill out your valence electron shell. Like, hey, can I have an electron? No. Like, hey, you want one of these? No. Kind of reminds me of American Suburbia. Like, hey, can I borrow? Go buy your own. Hey, do you want one? I don't know what you did to it. No. Like, everybody's like, stay in your lane. We're just. Okay. Good? All right. So, crystal lattice is how the molecules bond together and form like more like bigger things. So one big distinction between chemistry class and physics class: chemistry focuses on an atom or like the molecule, just like individual. Physics and at this level looks at macroscopic things. So things that you can see with your eyes, hold in your hand. Okay, so like quadrillions of electrons and protons. Okay, so this is my illustration of crystal lattice. What this is not saying is you have 4 electrons and 1 proton. What this is saying is protons are in the nucleus, electrons are whirling around on the outside. This would be a neutral object. Okay, so let's say this is a neutral conductor. Let's say like a slab of metal. So like a 45-pound weight, like cookie that you do for weightlifting. Okay, it's neutrally charged. Okay, you have a negatively charged object. This is not an electron. This is, let's say, a bowling ball. It's negatively charged. What happens when you bring a negatively charged object near a neutral conductor? What goes on microscopically inside the conductor? Here are your options. Protons go near, electrons go away. Protons stay put, electrons go away. Electrons go near, protons go away. Electrons come near, protons stay put. So think. Thumbs up when you have a guess. Okay. One cool thing about these units is you've not been exposed to them that much to this stuff, and so you don't have many misconceptions or preconceived wrong ideas, which is nice. So I just tell you, here's how it goes, and you're like, okay. So I won't need to, like, I want you to guess, but then I'm just going to tell you what the right answer is because you don't have a whole lot of background knowledge to, like, draw from. Okay. So, correct answer is beautiful butterflies. Okay. The reason why it's not A is because protons don't move. Protons are stuck in the nucleus. Electrons are the only thing that can move. But this is a sea of electrons, and so electrons are able to migrate across the whole metal slab.
Why don't they go towards the negatively charged ion?
Because like charges repel
Like charges what?
repel each other.
Okay, well, why does the proton, you said the protons don't move?
Protons are stuck in the nucleus. So the crystal lattice prevents that from, it's not a gas or a liquid.
Electrons, why do they?
Because they're flowing around, like they're in the orbits, they're in.
Oh, they're not.
Yep. Good? Okay. In chemistry class, you talked about water, H2O. Oh my goodness, that was a horrible water molecule. You talked about water molecule being polar. This side was partially positive, and this side was partially negative. As a whole, the molecule is neutral, but it had one side that was partially, it kind of tended towards positive, and this tended towards negative. Okay. In this arrangement, we would say that the metal slab has been polarized. Okay. Overall, it's still neutral. We haven't lost any protons or electrons. But this side is partially negative. This side is partially positive. Been polarized. Okay with that? Okay, still neutral, just polarized. All right, so that's a vocab word for you. Polarized. So if you have a insulator, slab of plastic, and you bring in a negatively charged object, what happens in the insulator? Here are your options. Nothing happens. Here the electrons run to the far side of the molecule, and that happens throughout the whole slab of plastic. The electrons run to the far side of the plastic, protons stay put, or the electrons run to the far side of the molecule, but that effect diminishes as you go away from this negatively charged object, and over here there's no real response, just locally. Thumbs up when you have a guess. Correct answer is dangerous dinosaurs. Okay, so in the suburbia analogy, these electrons are plastered against their fences in the backyard, like, no, let me out, let me out. And they're like, no, stay in. All the other neighbors like, stay in your fence, don't even come over. But that effect diminishes as you go away. It's kind of like, oh, you just had a house fire. That stinks. Glad it's not me. Okay, so it's just like a localized thing. Good with that? Reese? So a conductor would look like this, where electrons run all the like it's a sea of electrons. They're not bound to their molecule, and they can travel throughout the entire slab of metal. Versus here, they're bound to their molecule. Good. All right. So if a neutral object, will a neutral object be attracted to a positively charged object that is brought close to it? Correct answer is actually it will be attracted. Why? Because of polarization. Okay? When you have a balloon, you know the trick where you can rub the balloon on your hair and then it sticks to a wall? Okay? So you charge the balloon, the wall is neutral. But when you bring the charged balloon next to it, the electrons in the wall run to the far side of the molecule, and the protons are closer, and so that force of attraction is greater than the force of repulsion. So in chemistry, a neutron doesn't do anything to a proton, but in physics, because they're macro-sized objects, you get this polarization effect, and you can get an attraction. Okay. Have a conversation.
C is possible because you can figure that out.
Correct answer is F. Oppositely charged and also attracted to neutral because of polarization. We'll call that good for today. Got a pre-quiz due on Friday. 53. Zach.
You should probably look on your chair, or like the chair that
You usually are not charged.
Okay. We're not. We don't have it. Unless we carry a charge sometimes.
Temporarily. I mean, we'll talk about it tomorrow, but if you ever get shocked, something is charged.
How was your 4-day weekend?